Hi. So for this video, since we have already finished discussing the solutions of first order ordinary differential equations, let us now proceed with some application problems involving first order differential equations. So the first application that we will be discussing is growth and decay. Okay, so this pertains to growth or decay of any substance, or it could be growth of a population. Okay, so anything that is growing, okay, and can be quantified. So growth of population, what else? Cell multiplication, bacteria colony. Okay, so the rate of growth of those things. So we can also use it on decaying substances. Okay, so say for example radioactive decay. Okay, so growth and decay, so for those things that changes, okay, so their quantities change. So this is not general, okay, so this is not universal, I mean. So but most of growth and decay problems follow this law, okay, or this condition, that the rate of growth or decay is proportional to the amount present. Okay, so if we let Q as the amount present at any time t, then dq over dt, or the rate, okay, so this derivative is the rate of change of Q, which is the amount present at any time with respect to t. Okay, so the rate of change of the amount present is directly proportional to the amount present. Okay, so what does this mean? So if we say this is a rate of growth, okay, so the larger the amount present, so the faster the rate is, and the smaller the amount present, so the smaller the rate also. Okay, so because we have a direct proportionality between the rate and the amount present. Okay, so this is the proportion expression. Okay, but if we transform it into its algebraic form, then we will replace the proportionality sign with equal sign, and then we add a proportionality constant. So let's say we add k as our proportionality constant. So we will have dq over dt is equal to kq. Okay, so this is now an ordinary first order ordinary differential equation with variables q and t. Okay, so to find the solution of this differential equation, we can see that it is simply variable separable. So we can transfer q in the denominator of dq and then cross multiply dt on the other side. So this will become dq over q is equal to k dt. Okay, and then integrating both sides, so then we will have integral of dq over q, that is ln of q is equal to kt plus c. Okay, so that c, we can solve for it. Okay, so using an initial condition. Okay, so that at time is equal to 0, the amount present is equal to the initial amount, okay, or q sub o. Okay, so this is initial amount. Okay, so at time is equal to 0. So that is when at the start. Okay, so at time is equal to 0. Okay, so substituting t is equal to 0 and q is equal to qo or q sub o. So that will be ln of qo, or the initial, is equal to k times 0, k plus c. Okay, so therefore our c now is equal to ln of qo. Okay, so substituting that back into our general solution, then our particular solution will be ln of q is equal to kt plus ln of qo. Okay, so to simplify this, so as you can see, this involves logarithm, so we can express it into exponential form. But first, let's simplify. So transposing ln qo on the other side, so this will become ln of q minus ln of qo is equal to kt. Okay, so using the laws of logarithm here, so this will become ln of q over qo is equal to kp. And then, since, if you remember, we have ln of, say for example, ln of x, so that is actually equal to the logarithm of x to the base e. Okay, and then if we have logarithm of a to the base b is equal to n, so that's equal to n, then b raised to n is equal to a, right? So we can also apply that in here. Okay, so we have base e. Okay, so base e, if we use e here instead, so that we can have a better log of e, a is equal to, so log of a to the base e is equal to n, so therefore e raised to n is equal to a. Okay, so in this case, our n is kt, our e is e. Okay, so the base of the natural logarithm, since ln is equal to the logarithm to the base e, then a is q over qo. So therefore, e raised to kt is equal to q over qo. Okay? Or, if we transpose qo on the other side, then qo e raised to kt is equal to q, or we'll have q is equal to qo e raised to kt. Okay, so this is the the simplest form of the solution. Okay, so in solving problems involving growth and decay, and if it follows this rule, then all we need to do is memorize this formula. Okay, so all we need to do is memorize this formula. So in problem solving, you don't need to derive anymore the formulas using differential solutions to first order differential equations. Okay, so now after this, so we have also another concept which is called the half-life. Okay, so the half-life, that is the time. Okay, so time for which the amount present at any time is equal to 1/2 of the initial amount. Okay, so let's say that is the 1/2. Okay, so the half-life is, so we just need to find time at q is equal to 1/2 qo. Okay, so from here, so we will substitute q is equal to 1/2 qo. So here, so q is equal to qo e to the k power of kp. Then at t is equal to t1/2, or the half-life, okay, q is equal to 1/2 of qo. Okay, so therefore, substituting, so q is equal to 1/2 qo, so 1/2 qo is equal to qo e to the power of kp. Okay, so as you can see, so common factors, qo, we can cancel that out, and then 1/2 is equal to e raised to kp. So, sorry, this is already t1/2. Okay, so because we substituted, q is 1/2 qo, and then t is t1/2, or the half-life. Okay, so solving for t1/2, so we can take the logarithm of both sides. So this will become ln of 1/2 is equal to ln of e raised to k t1/2. Okay, so using the laws of logarithm, so we can transfer k and t1/2 as the exponent of the natural logarithm. So ln 1/2 is equal to k times t1/2, and then times ln of e. Okay, so but we all know that ln of e is equal to 1. Then solving for t1/2, divide both sides with k. Okay, so we can cancel out k. So then what will remain is t1/2 is equal to ln of 1/2 over k. So half-life, okay, so half-life, its formula is t1/2 is equal to ln of 1/2 over k. Okay, so remember that one. Okay, so we can also there are also other expressions of this. So it could be negative ln of 2. Okay, so because ln of 1/2, right, that is equal to ln of 2 raised to negative 1. So therefore, using the laws of logarithm, so transferring that there, so it will become negative ln of 2. Okay, so the half-life can also be expressed as, so let's just write this here, negative ln of 2 over k. Okay, so you just memorize these formulas. Okay, so these formulas for solving problems involving growth and decay. Okay. Okay, so let's solve an example problem. So a certain radioactive substance has a half-life of 36 hours. So find how long it takes for 90% of the radioactivity to be dissipated. Okay, so this is a decay problem. So radioactive decay follows the rate law, okay, that we have stated earlier. So this one. So radioactive decay follows this. Okay, so therefore it follows this, and its half-life is this. Okay, so it is said that its half-life is 36 hours, and we are tasked to find how long it takes for 90% of the radioactivity to be dissipated. So how long it takes, so it pertains to time when 90% of the original amount is dissipated or gone. Okay, so if 90% of the original amount is gone, then only 10% is remains. Okay, is remaining. Okay, so remember that Q, or this one, this is the amount present. Okay, so therefore if 90% have dissipated, so therefore only 10% are present. Okay, so given, so we have half-life, so our symbol for half-life is T1 half, so that is equal to 36 hours. What else? We are also given that 90% of the radioactivity already dissipated. So therefore, Q, okay, so our Q is only 10% of the original amount, or 0.10 of QO. Okay, so we are required now with the time. Okay, so solution. So from here, okay, so from the formula that we have derived earlier, so we have Q is equal to QO e raised to KT. Okay, so we are looking for the time. Okay, so solving for time in this form, so we can divide both sides with QO, okay, to return it back to the logarithmic form. So therefore Q over QO is equal to e raised to KT, right? So taking the logarithm of both sides, we will have ln of Q over QO is equal to ln of e raised to KT. So again, using the laws of logarithm, we can transfer this as the coefficient. So ln of Q over QO is equal to KT ln of e. But we all know that ln of e is equal to 1. Then, solving for t, we divide both sides with k. So therefore, t now is equal to ln of q over QO over k. Okay. So however, we don't have the value for the constant k. But we know from the given half-life of 36 hours, so we know that half-life is equal to ln of 1/2 over k. Okay. So since t1/2 is equal to ln of 1/2 over k, then cross multiplying, we'll have k is equal to ln of 1/2 over t 1/2. Okay, so since we have t of 1/2, so t of 1/2 is t1/2, or the half-life is 36 hours. So therefore k is equal to ln of 1/2 over 36. Okay, 36. So if we include the units, so it's per r. Okay, so ln of 1/2, that is unitless. Okay, so if we convert this into decimal, so we'll have k is equal to, so ln of 1/2, oops, so ln of 1/2 divided by 36, so this is negative 0.019254 088 per r. Okay, or Or we can simply use this, ln 1 half over 36. Okay, so it depends upon your preference. Okay, so now we can solve for time t. Okay, so ln of q. So earlier we have discussed that the q, the amount present, is equal to 10% of the initial amount. So it's only 10% again because 90% have been dissipated already. So time now t is equal to ln of, so q is 0.1 of qo over qo all over k. So our k is ln of 1 half over 36. Okay, so we can cancel qo. Then t now is equal to, so let's solve that. So ln of 0.1, ln of 0.1 divided by, we have ln of 1 half is 0.5, right? Divided by 36, but we should place this inside a parenthesis. Oops, insert. Okay. Okay, so again, so ln of 0.1 divided by ln of 0.5. Okay, so times 36. So the answer should be 100, around 119.6 hours. Okay, so after 119.6 hours, then 90% of the radioactivity has dissipated already. Okay, so 119.6 hours, that is divided by 24, that is about 5 days. Okay, so that's it. So all you need to do is practice solving problems involving growth and decay. So the concept of growth is also the same. Okay, so that's it.